Oh, that was pretty fun.
Here we go. All right. So we are going to learn probably a 10th way to solve systems of equations. There are so many ways. It's just insane. So the way we are going to learn today to solve a system of equations is called Cramer's rule. And Cramer's rule is sometimes taught really poorly because people try and teach it just using equations and not matrices, but it is fully a matrix topic because it is completely dependent upon knowing what a determinant is and how to calculate determinants. And so, this is a lot of stuff. Probably useful if you want to read very closely. But essentially, if A has a non-zero determinant, you know there will be a unique solution. Okay, you know it's not a singular matrix. The answer is the column vector. I don't know why they wrote it that way. They could have just written it as the column vector instead of that transposed. So this gives you the individual answers. So x1, x2, x3. So what you do is you find the determinant of the coefficient matrix. That's going to be your denominator of this equation throughout when you're calculating x1, x2, x3, or if you're doing x, y's, and z's, x, y, and z. And then on top, you have the determinant of a new matrix you create. And the way you create the new matrix is you take B and you replace it with what you're trying to find. So if you're trying to find x1, you replace the first column with B, and you find the determinant of that. If you're trying to find x2, you take B and you replace it with column 2, and you find the determinant of that. And then you can have the answer. So it makes much more sense if we actually do it. So the words are not as useful as the doing of the problems. So we're going to do a few, but once you know it, this is so cool. No. Cramer does. Mr. Polster may have mentioned it.
I think, would it have been in series?
Cramer. I think it was a Cramer with a K.
Yeah. Is it like K-R-E-M-E-R? That's the thing?
No, that's
That sounds like a block.
yeah, I agree with that. No,
I
we
think
did
it's
K-R-A-M-E-R. Yeah, we did. Cramer.
There's something like K-R-E-M-E-R that's in my file. Oh.
All right.
Cramer is
So, just to give you a sense visually, ladies and gentlemen, of what I was talking about, if you were to find x1, which is the answer to this matrix equation where A is that and B is that, x1 is the determinant of this matrix. And I want you to see if you can follow where these numbers are coming from. Divided by the determinant of matrix A. So notice, because I'm trying to find x1, I'm replacing the first column with the constant side, okay, which is B. And so it's the determinant of A1. So this is defined as A1 because we replace the first column of A with B. The determinant of that divided by the determinant of A would be x1. And then for x2, you would replace the second, column with 10, 11, 12. And then for x3, you'd replace the third column with 10, 11, 12. And then you get the answer. So let's do it. We're going to do it with a 2 by 2 first because the math is easier. So here A is going to be 4, 5, 1, 2. Because that is the coefficient matrix. X1 well, I don't have to write it, I am, just to define it, is x1, x2, and b is 6, 7. So x1 is going to be the determinant of A on the bottom of the fraction, and the top of the fraction is the determinant of A1. And A1 is 6, 7, 1, 2, because I replaced the first column, or the x1s, with the 6, 7, the constant terms on the right side of the equation. So the determinant of A is going to be 3, because it's 8 minus 5. So this is going to be 12 minus 7 over 3. So that is x1. x2 is the determinant of A2, which I achieved by replacing column 2 with 6, 7 over the determinant of A, which is 3. So you have 28 minus 30 over 3. So that's x2. So our answer is 5/3, -2/3. So it's all about replacing the column that you're trying to find with the solution column. So you're replacing those coefficients. Any questions on that? And I'm sure there's a proof in the book about why this works. I haven't quite thought about it yet. So Cramer's rule is really neat when you have a lot of variables in a system that would make row operations yucky, and also a lot of things would be yucky with the S's. So if you want to consider a system and you wanted to determine when it has a unique solution, you first can find the determinant, because we know the determinant has to not equal 0 in order to have a unique solution. So the determinant of our coefficient matrix is going to be 12s squared minus 3s. And that cannot equal 0 if you have a unique solution. So I'll just factor out the 3s. So s cannot equal 0 or 1/4. So the first part of the problem, determine the values of s for which the system has a unique solution. So s is all values except 0 and 1/4. Or you could write it a little more mathy. Then it says use Cramer's rule to describe that solution. So, go ahead. Okay, so if we write this in terms of matrices, this is 2s, 1, 3s, 6s.
Oh, okay.
So the determinant of this cannot equal 0 if you have a unique solution. Never be sorry, because for everyone with that question, there's 6 other people that do, and stay mute. So thank you. I just have coffee and just go fast for no good reason, so please do that. Okay, so now I'm going to find x1, and that solution is going to be in terms of s. S is going to be a part of the answer. So x1 is going to be the matrix A1, which is represented by replacing 1, 2 with column 1. So it's the determinant of A1 over the determinant of the system. And the determinant of the system, the coefficient matrix, is 12s squared minus 3s. So x1 is going to be 6x minus 2 over 12s squared minus 3s. And I think on your test, I changed these to m's because I got really annoyed with the s's in the 5 situation. So for x2, we're going to change column 2 with the solution vector 1, 2. Other questions?
2s and 3s. So 2.
So I would get 4s minus 3s, which is just s, over 12s squared minus 3s. And since we already stated the restrictions on s, we can reduce x2. But we want to make sure we say that s cannot equal 0. And negative 1/4 because the 0 doesn't look bad in x2 if we reduce it, but we should because we did state that that was the restriction on s for a unique solution. Questions? Isn't this fun? Totally different way to do it. Okay. I also told you that we would find a totally different way of finding matrix inverses. And that would be doing these using cofactors. And so we're also going to be learning a bunch of new vocabulary words right here. So this is kind of the precursor to the result. The result of this theorem is a new way to find matrix inverses. So you are being focused. The inverse of the matrix is 1 over the determinant, which is something we're used to in a lot of our inverse equations, times the adjugate, that's that A dj of A. And this in green, sorry, is the transpose, so this is all how you find that adjugate. Adjugate is a new word for us. The adjugate is the transpose, so that's something we can forget to do. It is the transpose of the matrix cofactors called the adjugate or classic adjoint of A. Okay? So you create a matrix of cofactors. And cofactors are the results of finding all the many matrices in a matrix that is possible. So you do all the many matrix operations. You apply all the plus minuses in the plus minus checkerboard pattern. And that is the cofactor matrix. You transpose it. So rows become columns, columns becomes rows. And then you multiply it by 1 over the determinant. And then you have the inverse. It sounds like a bunch of gobbledygook just coming out of my mouth here, but it's really cool when you do it because you can find the matrix inverse of a 3 by 3 without elementary row operations, without a graphing calculator, without all these things, just by doing some multiplying and subtracting over and over and over again. It's repetitive, but it's less creativity and more just do it, which can be nice. Okay, so in lower dimensions, we know that this is the case. You guys learned this as freshmen, the definition of an inverse. But it actually is fully related to this cofactor method. The reason that we switch the A and the D and negatize the B and the C? We negatize the B and the C because the checkerboard pattern, okay? We switch the D and the A because these are actually the cofactors, and we're taking the transpose of it. Now this is what it looks like in 3 dimensions. The inverse of matrix A, which is defined by the letters A through I in terms of its elements, is 1 over the determinant of A times the transpose of the cofactors. And this is how you find all the cofactors. Okay. So, to find A's cofactors, so here, do you guys see how A is capital A? Capital A represents the cofactor of A. So what that is the determinant. If you go to A and you cross out the row in the column, you generate the mini matrix. And the determinant of that mini matrix is capital A. Capital B, I cross out the column and row that B are in. It generates the matrix DFGI. So the determinant of that matrix is DI minus GF. But because B is a negative in our checkerboard pattern, it's negative, sorry, where am I? Negative DI minus FG. So that's B's cofactor. Okay, C's cofactor. Cross out row and column that C are in. It's DH minus EJ. EG, right here. But we're on the positive. It's plus minus plus. And then we just go down to the next row. Do you guys want me to keep going, or would you rather do it with numbers?
Margaret speaks for the entire class. We will do an example.
Okay, so here, first let's find the determinant. That's generally always going to be your first step. So let's practice our determinating. That's a good word for that. And let's get 9.
Wait, isn't it 37? Yes, and then you make -1. 20 equals numbers. 37. Oh, flip.
Oh, well, that's nice. So 1 over -1 times. Now we're going to find all of the cofactors. So it might help us. I don't know what will help us the most. So A, B, C, D, E, F, G, H, I. So let's just find the cofactor matrix. So A, ooh, I'll use colors here. A, I cross out the row in the column that the first is in. And then I find the determinant of that matrix, which is 5. Okay, so capital A is 5. Then I keep going down the road. B, cross out the row and column that B is in, and I get -2. But in my checkerboard, do you guys know how I'm on a negative? So this is 2. C, cross out the row and column C are in, so you get 0 minus 4, and I'm on a positive, so it's -4. Now I actually like crossing them out and just erasing because it just makes make less mistakes. So here is D. You have 24 minus 21, but then you have to make that negative because you're on a negative. And please stop me if you're thinking I did something wrong or you have a question. So we have 12 minus 14 is negative 2, and we're on a positive, so that stays negative. Switch this down. Okay. 9 minus 12 is negative 3. We're still on a plus, so that's negative. Minus plus minus.
Nice, right?
I need to make these segments different so I can just move them. Oh. G, 6 minus 14 is negative 8. I'm on a plus. 3, I'm on a minus. 6, I'm on a plus. So the inverse is 1 over the determinant, 1 over negative 1 times the transpose of this. So when I was doing this earlier to like practice, this is the part I forgot. So it's the like everything is correct. You do all the cofactors, it's 1 over the determinant, and you have to transpose this. So the transposition of this is rows become columns. So the first row is the first column, second row is second column, third row is third column. And if your scalar quantity on the outside is bad, leave it out. In this case, it's easy, so you can put it in there.
The more I understand it, I have no idea what it is. Oh, yeah.
Okay, did anyone check this versus a calculator or, I mean, I can look at my paper.
I did a transposition for a second.
Oh,
How are we not supposed to make any better? That's just so long.
No, I know, but it's okay.
alright.
I just remember myself.
And I mean, if you get something wrong, it's not gonna be like 8 points or 0 points. 8 points and a half.
Sounds like a problem set.
Hey, I can start taking off full points.
Good.
Problem set.
Good.
I did not.
I did not hit her.
I don't think you
I
realize
did
how
not.
deep thinking about this grade.
Oh, hi, Mark.
Okay, questions?
Director. You understand. It's the room.
Well, we can all be good. Apparently we can't. Like talk about it.
Yeah. I did not hit her. I did not. Oh, hi, Mark.
Are we good? Okay, so 1 over the determinant. You find all the cofactors and you sure to keep track of the plus minus, and then you transpose them. Okay. You might want to just convince yourself why that dA, negative B, negative C works with the cofactor depth. Like, if you do it, like if we have time at the end, it's super cool. You're like, that's where that comes from. Finding the inverse of a 2 by 2, the rule you learn as a freshman. So, okay, so determinants help you to find the area of a 2 by 2 parallelogram or the volume of a 3 by 3 parallel pipette. The way it works is you define your geometric shape by 2 vectors. So if you're in 2D, you're going to define your parallelogram by 2 vectors. Make sure you don't define them by the vectors that are equal, because that's not a parallelogram, that's going to be just a ray or a line segment.
Right.
So you're going to define your parallelogram with two vectors. You'll put them in a matrix, vector 1, vector 2, and the absolute value of the determinant of that matrix is the volume of that parallelogram. It's super easy. Is there a question on that? If you have a parallelepiped, you need 3 vectors to determine a parallelepiped. You have the 2 vectors, which essentially determine the parallelogram in 2D space. So by parallelogram, you have to like do this and like that. That's your parallelogram in 2D space. But then to make this 3-dimensional, you need a 3rd dimension to know how tall it is. So these, or it could be going this way too, it could be slanted. So the volume of this parallelepiped is, do you remember what we called it? I think that's right. Yeah. Yeah, good job.
I thought you were just going to say close. That's pretty good, Marco.
Thanks, Mark. I also thought she was going to say close.
Yeah.
And the reality is, I think so. It sounds good. Yeah, triple scalar product.
It was like the scalar product from
Yeah, well, it's definitely scalar, because we're going to get a scalar quantity from the dot product.
Excellent. That's just for the what day is it?
It was like, oh, that was like September.
It was a long time.
Well, it was September, was it? Yeah,
I think that's October. Yeah.
I think it's October.
Or like late
In September, we had really bad.
Scalar triple product.
All right, so we're going to find the area of this parallelogram using vectors and using matrices. So we have 0, -2, 6, -1.
Just did that one.
It was actually September 12th, so we were
It's a what?
I didn't.
Let's see his hopes.
Oh, that experience.
That's not cool. No, that's right.
Okay.
that's
I think-
You gotta
No, that is good.
No, you gotta move your bottom right one over one.
Yeah, because it's over 3.
And it's 6, -1, not
Yeah.
5, -1.
Oh.
Okay, there we go.
Good save, Rohan.
No, well, that's not, no, yeah.
That looks better.
Oh,
It still looks a little off kilter.
Alright, well, I
Some
that
people-
great, such a long.
Okay,
Some people just want to do it.
so you're going to write the components of 2 vectors that define the parallelogram. They can be any 2 vectors, but they can't be the same vector, because that would be not a parallelogram.
That's not sure where it's.
That means the same thing.
Wait, do they?
Yeah.
Otherwise they'd be parallel.
Well, you can move vectors wherever you want, can't you?
Yeah, but just in terms of the drawing, like if you're trying to,
But wouldn't it work with the matrix no matter what?
well, vectors are everywhere, but when you then arrange them, you arrange them head to head to create your parallelogram.
Right, but like when you're actually multiplying them, does it matter? Or does it not? Like, you just plug it into the matrix?
There are only 2 vectors which determine the parallelogram,
Right.
right? So you're saying the order in which you arrange them?
No, I'm just saying like, because right now we have them arranged so that like the numbers correspond to a vertex. But I think we have the vectors like all over the place, like on the page.
They don't though.
Right now they don't, but I'm saying could you still get a like a parallel, like the volume of the or area of the parallelogram if they're separated? Or,
What do you mean if they're separated?
meaning like, because you know how vectors can like exist anywhere in space, they're just like supposed to be like a connection of
Yeah,
points.
because this parallelogram will have the same volume wherever it is.
Right, my
Or
question is like, what if the
area.
vectors aren't attached at that point?
Then it's not a closed shape.
Right, but could we still like get it if we plug it in and find a determinant?
Well, it wouldn't be applicable to area if you didn't close, if you didn't put the two vectors head to head and then do this. Because essentially, if I give you two vectors, they're just two arrows floating in space.
Right.
And if I say find the area, that makes no sense. If I say find the area of the parallelogram defined by attaching two vectors head to head, and then,
Okay, all right, yeah.
you know.
Okay, that makes sense.
So this vector is -3, 3. Because I go 3 over 3 up to get there. And then this vector is 1, 2, 3, 4, 5, 1. Aw. It was one more. So,
Oh, the thing when you erased it, it was that one.
sure, it's my fault.
Yeah, right.
Okay, so I get -3 minus 18. The determinant's going to be -21. So it's 21 square units. It is defined as the absolute value of the determinant. So be sure you do take that absolute value. We are not trying to consider negative area in this class. Questions? We consider the effect a negative determinant has on the orientation of a shape. So if the determinant is negative, we do consider that, and its absolute value will affect the area. But
It can with area though, right? Like if you're integrating and it's like under.
so that's for conceptualizing calculus. But if you're talking about actual
Yeah. Negative area.
figures,
Well, just like,
it stops making sense. But it makes a lot of sense in terms of, going below the x-axis, but it's not really physically a thing.
Right.
And that's where black holes are, and that I don't know enough about to talk about.
So,
I just